Hello calculus fans, and welcome to section 3.10 where we talk about linear approximations and differentials. So it's often useful to approximate complicated functions with simpler ones that are easier to work with but would still give us the accuracy we need. So suppose we have this function y equals f of x, and we're interested in the value of this function around this point A. Well, maybe for some reason it's difficult to work with this function at this point A. This will actually be a lot easier to explain when you're in Calculus 2 and you're doing integration. Then it's really easy to see where a linear approximation of a function is much easier to use than the original function. But we'll come up with some examples here too. But let's just say for whatever reason this function is hard to work with, but we want to approximate the value of the function at A. So the idea here is maybe we can come up with a tangent line. So we'll come up with a line that's tangent right at that point A. So we've got this line here, tangent to this curve at point A. So this red line has the same value, the same y value as this function at A. So that point there is the point A and f of A, right? Because we've got the x coordinate is A, so we've got A. The y value is just going to be the value of the function at A, okay? So if you think back to the good old days in algebra class, you have probably seen this form of an equation. Here's the slope here. So this is the point slope form of an equation, right? You've got a point x1, y1, and the slope m. So if we come up with the equation of this red line, this tangent line here, and we'll even give this a name. We'll say this line is y equals L of x. So L for line is a straight line. So if we plug this in, we've got this point x1, y1, right? We can find the slope, because isn't the slope of this tangent line at A, isn't the slope of a curve or the slope of this tangent line equal to the derivative of this curve? You take the derivative of this function and plug in A, that gives you the slope, right? Because remember, the geometric equivalent of a derivative is a slope, right? Slope of a curve. So we could fill these values and we could say, okay, so y minus f of A equals the slope. The slope is f prime of A, right? The slope of the curve at A, or equivalent to the slope of the tangent line at A, is just the derivative of this function evaluated at A. And then we go x minus x sub 1, which is A. And then we could easily just solve this equation for y. If I were to add f of A to each side of the equation, we get y equals f of A plus f prime of A times x minus A. And this is the equation of the tangent line to the curve. It's the equation of this red tangent line to the curve. So continuing here, we are using the tangent line to approximate the curve y equals f of x when x is near A. Now you can see this is only going to be a good approximation when x is near A, because remember, the value at A, when x is equal to A, the curve and the tangent line are equal to each other here. They both share this point. So as we get further away from A, we get further out here, there's errors here, right? The difference between the function and the straight line become bigger as we go further away from A. So we want to be close to A for this tangent line approximation. Okay, so the approximation f of x is approximately equal to f of A plus f prime of A times x minus A is called the linear approximation, or the tangent line approximation of f of x at A, right? So it's it's only going to be accurate, it's only going to be close near a. So we have to be close to a. And also, the linear function L of x, which equals f of a plus f prime of a times x minus a, is called the linearization of f of x at a. So notice these are really the same thing, right? This is saying this tangent line here, this equation of the tangent line, it's approximately equal to the function as long as we're near a. And then this is just saying, see, this is the same as this. This is just saying, sometimes we'll just call this L of x, or the linearization. So sometimes it would be said that we linearize the function by coming up with this tangent line approximation, or the linear approximation of the function at a. Now, one thing you'll see later when you're in Calculus 2, you'll see that really what we're doing is a Taylor series. We're doing a first order Taylor series. And this technique will be developed a lot more in Calculus 2. And in fact, Taylor series are one of the most important things you'll learn in the calculus sequence. But even as a linear approximation, even though this is we're just using a straight line, you might think, well, when would that even be used? But they're actually used quite often. In fact, the GPS system of satellites has been operational since 1994. There are 32 satellites up there in that system right now. There's not all being used. I think they use like 24 of them at a time, but there's some up there for redundancy. And they are up there, they are moving around at 9,000, or right around 9,000 miles per hour, which is about 2.5 miles a second. So they are really moving. They're about 13,000 miles up. And when you're that far away and you're moving at those speeds, it actually affects the clock times. And for these satellites to work correctly, they have to communicate with each other, and the clock times have to match. So there's a formula for time dilation from special relativity, and those satellites actually just use a linear approximation of the time dilation formula. And so just a linear approximation for something like that is all it takes, and it works just fine, obviously. In fact, I believe it was said that the error using this linear approximation gets you to within 1 millimeter of any location using the GPS system. In fact, if you want to hear more about that, there's MIT OpenCourseWare has a video, and Professor David Jerrison talks about it. The information is here. If you start the video at the 30-minute mark, it lasts about 5.5 minutes, where he talks about using linear approximation in the GPS system. So if you want to hear more about it, go ahead and check that out. But not until you get done with this video, of course. This video is going to give us all the goods we need to make sense of this stuff. And then this is just a really good video, I think. We'll repeat a lot of these things, but at the 30-minute mark, you can hear about the GPS system. Okay, but for now, we've got our first example, and it says to use a linear approximation to estimate the square root of 25.1. First thing to notice is we've got a function. This is the square root function, right? It's the square root of 25.1. So it's a square root function. And what we want to do, the point A that was in our picture up there, the point A, we want that to be a point near this that we know the answer to. So this one's kind of obvious. We know the answer to the square root of 25, right? The square root of 25 is, of course, 5. So we want to center our approximation on something we know. So we'll center it at 25 because we know the square root of 25. So A will be 25. So basically, we want to just think of, okay, we're gonna use our function is going to be the square root of x, and A is going to be 25. So we'll keep this in mind the whole time. And then we just are going to use a function to approximate that. We know that f of x is approximately equal to f of a plus f prime of a times x minus a. Okay, so let's write some of this down here. So f of x is the square root of x, which is x to the 1/2. I'm writing it like that because we have to take the derivative, right? Because we've got a derivative here, so we need to take the derivative of our function. And this will happen every time, so we take the derivative. And we have the power rule here, so we get 1/2 x to the 1/2 minus 1, which gives us 1/2 x to the minus 1/2. Now we're going to be plugging some numbers in by hand, so I want to write this in a way that's a little easier. So as we've seen before, this is the same as 1/2 times 1 over x to the 1/2, right? Because we could write this as 1 over this thing to the positive 1/2. And x to the 1/2 is just the same as the square root of x, so this is really equal to this, right? Because you multiply fractions straight across, and you get this. So that's f prime of x. And then we could say, okay, so what about f of a? Well, f of a is f of 25, and f of x is the square root of x. So this is just going to be the square root of 25, which is 5. And f prime of 25, well, here's f prime of x. F prime of 25 is 1 over 2 times the square root of 25. 1 over 2 times the square root of 25, which of course is 1 over 2 times 5, which is 1 over 10. And once we have this, then we can just fill in what we need. So we're basically saying f of x, and we know f of x is the square root of x, right? It's approximately equal to let's see, f of a, which is going to be 5, plus f prime of a, which is 1/10, times x minus a, and a is 25. So we've got our linear approximation here. The square root of x is approximately equal to this as long as we're near a, right, which is 25. So then to approximate this, and we can say, okay, so the square root of 25.1 is approximately equal to 5 plus 1/10, 25.1 minus 25. Okay, and what that is equal to is 5 plus 1/10. Well, 25.1 minus 25, that's just 0.1, right? This is 0.1, which is also equal to 1/10. So we have 1/10 times 1/10. That's equal to 5 plus 1 over 100. Right, 1/10 times 1/10 is 100, and that's really just 5.01. So here's our approximation. So if you want to compare this to, I guess what we would call the actual answer, I'll say that in quotes because we're going to still get an approximation, but I'm going to just use the TI 83 or 84 and punch in the square root of 25.1. And the TI 83 and 84 also use an approximation technique, but it uses something called the Cordic algorithm, which is kind of a pretty sweet algorithm, actually. Not one that's fun to do by hand, but it's well suited for calculators or computers. But using that, I'm just going to round here, but basically it says 5.00999. I'll just stop at that point, round it there. But you can see it's you know, our approximation, something we did pretty quickly by hand using a linear approximation. Not too bad, right? So this is the calculator's approximation. This one we just did by hand, so not too far off. But I know what you're thinking. You're thinking, sure would like to see some trigonometry, Kurt. Well, I knew you'd be saying that, so I put this problem in there just for you. This says find the linearization. So see, I'm using this different notation, different wording, so you'll see it. Find the linearization of f of x equals sine of x at a equals pi over 6. So they want us to linearize the sine function. So make a straight line that's close to the sine function at this one particular point. Okay, so we can use our equation L of x, which is f of a plus f prime of a times x minus a. Remember, this is just saying this is a straight line that's equal to this, and this straight line will be close to this. It's just like we did, very close to what we did before. We just said f of x is approximately equal to this. So just a different phrase is just saying use this notation L of x instead. Okay, same idea. We go through the same process. We find the function. This time the function is sine of x. We know what a is. So we can basically go through the same process as before. So f of x is sine of x. First thing we're going to have to do is find the derivative. F prime of x equals cosine of x. And then we want to find f of a. So f of pi over 6 is equal to the sine of pi over 6. And then f prime of pi over 6 is equal to cosine of pi over 6. Okay, so if you remember, you know, there's a couple ways to do these trig functions. Some of you learned the unit circle. Some of you learned the special triangles. Since we don't cover this in calculus, we just review it. I just always review the special triangles because I think it's just easier to review. So one way or the other, we have to be able to figure out the angles of these special, or figure out the trig functions evaluated at these special angles. So we've got 30, 60, 90, 45, 45, 90. And the way that you can remember these is just think in each case the shortest side has a length of 1. So in this case, since these are both 45s, these are going to be the same angle, so these will both be 1. So in this case, using the Pythagorean theorem, we get the square root of 2 here. So we get the square root of 2. And in this case, in the 30, 60, 90, we also get a 2 in the radical, or in the, 2 in the hypotenuse. And then we get this a square root of 3 down here. So this one, 1, 1, and then Pythagorean theorem gives us square root of 2. And this one, we just go 1, 2, 3, but the radical here is down here. Okay, so this is a 60-degree angle, which is pi over 3, right? This is a 30-degree angle, which is pi over 6. And those are just because pi radians is the same as 180 degrees. And these two are both 45 degrees, or pi over 4. Okay, so basically, if you just know what the sine and cosine graphs look like, at least on one period between 0 and 2 pi, and you know these two triangles, you can pretty much figure out any kind of trig question you're going to have about the special angles. All right, so for this one, sine of pi over 6, remember sine, cosine, tangent, SOHCAHTOA. That's the way most of us learn it nowadays. So pi over 6 for sine is going to be opposite over hypotenuse, so that's just 1 over 2. And cosine of pi over 6, cosine of pi over 6 is adjacent over hypotenuse, so it's square root of 3 over 2. All right, so that gives us that. And once we have this, we can basically just go back here and plug in our values. So L of x, the linearization of the sine function, is equal to f of a, which is 1/2, plus f prime of a, square root of 3 over 2, times x minus a, x minus, and a is pi over 6. Okay, so just like last time, you don't need to multiply this through there and get it into like y equals mx plus b form or anything like that. We can just leave it like this. And then if we need to evaluate it, if we need to like evaluate maybe something near pi over 6 or something near 30 degrees, like, oh, I don't know, how about 29 degrees? We can just leave this and then plug in the 29 degrees right here. Okay, so if you wanted to take a look at this and see if it maybe we should do that. Maybe we should take the graphing calculator and plug in y1 equals sine of x and let y2 equal this, and then zoom in on it and see if it looks like this straight line is just tangent to this curve at pi over 6 or at roughly 30 degrees. So if you take a look over here, I put in the calculator, I put the two graphs, sine of x and then our linear approximation. I changed the window to go between negative pi, it's covering up the negative sign there, but it says negative pi to pi, and then the x scale is just pi over 2. And then put the y values between negative 2 and 2. Then you can see, so here is negative pi, and the sine curve comes around, goes through the origin, comes back, and hits 0 at pi again. And then here's the curve. So pi over 6, so of course this is pi halves, so pi over 6 is probably somewhere around here. It does in fact look like they're tangent. So it looks like around here we're going to get a pretty decent approximation. So remember, this is pi over 2, right? Pi over 2 is 90 degrees. So halfway would be 45 degrees. We centered this thing at 30 degrees. So around 30 degrees, these should be pretty close, right? The tangent line should approximate the sine curve fairly well around 30 degrees. But look, like out here at 90 degrees is not very good, and as you go further out, the error gets really big, right? So these are only good on a certain window, and our window is around pi over 6, so that's where we centered it at. So around pi over 6, it should be fairly accurate. If we wanted to do some sort of approximation further out here, like, you know, at 100 degrees or something, then we would not want to center it here. We'd want to center it maybe at 90 degrees or something, again, where we know the answer to. Okay, so let's go ahead and look at the next part where we actually use this to approximate sine at 29 degrees. All right, so I just copied down what we got before. This is the function, right? We linearized the sine function. We got this. So basically we're saying the sine function is approximately equal to this, right? We linearized it. Up there we said L of x equals this. L of x meaning the straight line that is close to the sine function equals this, right? So it's just another way of saying the same thing. So 29 degrees, we need to work on this though, because we need to use radians. Because remember, the derivative of sine of x is cosine of x only in radians. If you use degrees, you have a multiplier, right? Because as we talked about before, when we did those proofs, we proved that the derivative of sine is cosine. It was based on some of those limits, and those limits were based on us using only radians. So anyway, if we've got sine of 29 degrees, we're going to have to change that. So 29 degrees is really 30 degrees minus 1 degree. And 30 degrees, we know that's really pi over 6 minus 1 degree. Well, remember, pi radians equals 180 degrees. So if I want to get 1 degree, I'm going to divide each of these sides by 180, right? Divide that by 180. And then what we'll get is pi over 180 radians is the same as 1 degree. Okay, so this means I need to subtract pi over 180. Now, there's a reason I'm not just converting, because as you know, if I wanted to, you could take 29 degrees and write 29 degrees over 1. I could multiply by 1 in the form of pi radians over 180 degrees, and I would just get essentially I get what this is as one term, right? But I'm going to purposely break it up this way because when we plug these in here, we're going to be able to get this pi over 6 to cancel. Okay, so I'm just going to purposely write 29 degrees like this. And then we can do this. We can say, okay, the sine of 29 degrees, well, that is the same as the sine of pi over 6 minus pi over 180. right? This is 29 in degrees, this is 29 degrees, and this is the same value but in radians. And then we can just punch everything in here, okay? So this is approximately equal to 1/2 plus the square root of 3 over 2. And now for x, this x value here, I'm going to plug in this, right? So I'm going to get pi over 6 minus pi over 180. But then I have minus pi over 6, right? So here's the x value. So now I go minus pi over 6, minus pi over 6. And you can see right away that pi over 6 minus pi over 6 will cancel. So we get that this is equal to 1/2 plus the square root of 3 over 2 times negative pi over 180. And this one, I'm going to go ahead and punch in the calculator, and we'll get 0.48488500053. Okay, so let's see what the actual value is. I'm going to put actual in parentheses because it's still an approximation, right? But using the TI 8384, if we go to sine, now my calculator is always in radian mode. So to get it into degree just for this particular problem, I don't want to change the whole mode. So we can hit sine of 29 and then go to hit the second button and then hit angle, and you'll see this. So hit the second button and then from there hit angle, and you'll be able to punch in that symbol. Actually, I guess the key says apps to get to the angle. So it'd be second and then hit the key that says apps, and that'll get you to the angle. And when you do that, you'll see our calculator says that this answer is 0.484809602. So again, it's not too bad, right? I mean, it's just a linear approximation. And of course, we're close to 30 degrees, so our approximation agrees at 30 degrees. They're exactly the same, because you punch in pi over 6, you get, this all goes away and you just get 1/2. So they're the same at 30 degrees. And 29 degrees is close enough so that they still agree to about 4 decimal places. So not too bad. Another topic we look at in this section, which is also used for approximations, is differentials. And you'll see differentials from time to time throughout calculus. So we'll talk about them right here, though. So up until now, we've been using Leibniz notation, dy dx, to represent the derivative of y with respect to x, right? dy dx. Contrary to its appearance, it's not a ratio. So it looks like a fraction, right? It looks like dy divided by dx, but we haven't used it that way. We've meant it as a symbol. This is a symbol that basically means a change of y with respect to the change in x, or in other words, y prime. So we've been using it as a single symbol. But what we're going to do now is we're going to actually treat it like it's a true fraction. So we're going to treat it like this is an actual fraction bar. And we're going to treat it like we've got these, well, or actually we are going to use two new variables, dx and dy, with the property that when the ratio exists, it's equal to the derivative. So these are separate entities now called differentials. And this is a true fraction of the differential dy divided by the differential dx. So what we have is something like this, or we had before, we'd say f prime of x equals dy dx. Well, now when we use differentials, remember this is a true fraction. It's dy divided by dx. So if I wanted to, I could multiply both sides of this equation by dx to get rid of this fraction. And if we did that, we would get dy equals f prime of x dx. Right, so all I did is treated this like a true fraction, divided both sides by multiplied both sides by dx to get dy by itself, and have f prime of x dx. So dy equals f prime of x dx is called the differential dy. So when we're talking about this differential dy, it's defined as f prime of x dx. And to introduce these geometrically, it requires a picture. So we've got this picture here. So if you notice this line here, this is the function y equals f of x. And we've got a point x here. And then we move it over a little bit. We add delta x to get this other point, and it comes up here. And you've got this red line, which is a tangent to the curve, the tangent to this function at this point. So then we've got, see this right here, this little gap would be delta y, the change in y. It's a change in y as x goes from x to x plus delta x. Y changes. So here's the y coordinate of this first point would be over here on the y-axis. The y coordinate of the second point is over here on the y-axis. So delta y is just a change in the y coordinates between these 2 points, right? Delta y. And likewise, this would be delta x. And this is called delta x. We're also going to let this be dx. So we'll call that dx also. And then there's a note. We have to make, actually, there's a couple notes here we need to be aware of. Take a look at the picture here and the notes. dy is the amount the tangent line rises or falls. So as x goes from here to x plus delta x, dy shows that the tangent line, the y-coordinate was here. As x goes over to here, now the y-coordinate of the tangent line is up here. So this change right here was dy. Okay, and then delta y is the amount the actual curve rises or falls when x changes by dx. So x goes from here to here. And the curve itself, the function, it had a y-coordinate of here when we were at x. We moved over here, and now the y-coordinate is up here. So this is the amount that the y-coordinate actually changed, right? So the y-coordinate changed by this much by delta y, and we're going to end up using dy to approximate this change. So over here, there's a kind of a big error, so we wouldn't want to, we want this to be a lot closer to x, but this is just to show what this is. So dy is the amount the tangent line rises or falls. Delta y is really the change we want. It's the actual change in y. But what we're going to end up doing is using dy to approximate delta y. And again, this is out far enough where you can see a big error. We would typically x plus delta x and dx would be a lot smaller. It'd be over here. So the little difference between delta y and dy would be much smaller. These two would be very close to one another. And now what we'll do, we'll walk through a little argument that makes it seem reasonable that we can use dy for a pretty good approximation for delta y as long as we're close enough to x. Or in other words, what I mean by that is as long as delta x is pretty small. So what we can do, first let's notice that delta y is actually just f of x plus delta x, which is that point, right? Isn't that point really f of this, f of x plus delta x? And then you subtract f of x, which would be that y-coordinate there. So if you subtract those two, you get delta y. Okay, so as we were talking about earlier, if you notice that delta y is just that y-coordinate, take away that y-coordinate, right? That would give us this gap, that y-coordinate over here, take away this y-coordinate over here. This y-coordinate is just f of that, right? Because you plug that x-coordinate in the function. So f of x plus delta x minus this y-coordinate here is just f of x. So you subtract that. Then also, if you remember before we had this limit definition of a derivative, now probably you've seen this more often with an h instead of 0. But it's really the same thing, right? This was an h, we had x, and then we had x plus h. So it's the same thing, we're just different notation. So dy dx was this. Okay, so that means because delta y is this, then we could go from this limit definition of dy dx. And just since this equals delta y, we have this. So when delta x is small, right, when delta x is small, because we know that this is the limiting value of this as delta x approaches 0. So when delta x is small, we could say this. When delta x is small, delta y over delta x would be about equal to dy dx, right? Because it's the limiting value. The limit of this as delta x gets really, really small is this. So we could say when it's small, so we haven't taken the limit, but just as it gets small, these two are approximately the same. Also, if you look in the picture, delta x and dx are exactly the same. So since these both denominators are the same, then we could say also, since dx equals delta x, we have delta y is approximately equal to dy. Just from up here, right? Delta y over delta x is approximately the same as dy over dx. And since those denominators are the same, we could say this. So what we're saying is, if you look at what this is the differential dy. This is the differential dy. And this delta y is the actual change in y. This is the actual change in y. And so if we're looking for the actual change in y, maybe we can just use dy. Maybe dy will be easier to find. We can use that, knowing that they're close. All right, everybody still with me? You made it through that? You ready to try one? I only asked because it looks like I lost 2 students on the way. They couldn't take it anymore. They got very sleepy. So, hope this didn't happen to you guys also. But unfortunately, they're going to miss out on the fun because now we can finally use differentials. So we're going to do something similar to what we did before when we used a linear approximation to do an approximation. So now we'll do a differential just to see how they compare. In differentials, as I mentioned, you'll see these from time to time in other calculus classes for different applications, but this is what we're using for here. So first we start off, we'll say, okay, we've got a square root again. We're trying to approximate the square root of 16.2, so our function we're working with is the square root function. This time what we want to do is we're going to think of the thing that we know the answer to. We know the square root of 16, so we're going to say, all right, x equals 16, but then delta x equals 0.2. So we're going to center our square root at 16, but then we're going to change x by 0.2 to get to 16.2. And remember that from our picture above, delta x is the same as dx, right? So then we can use a differential here. So the differential dy is equal to f prime of x dx. And remember that the differential dy is approximately equal to the actual change in y. So just to mention that again, so dy equals the approximate change in y. So as x changes from 16 to 16.2, here's a change in x, dy will be the approximate change in y, and y started at the square root of 16, which is 4. So as x changes by 0.2, how much does y change by? Well, dy will be approximately that change. So here we go through and we figure this out. So f of x is the square root of x, so dy is f prime of x, and we did that one earlier. So we know that dy is equal to 1 over 2 times the square root of x dx. So then what we do here, again, this is dy, right? This is the approximate change in y. Now we can plug in our values. So we know x is 16. We know dx, which is the same as delta x. Remember that from our picture above, dx is the same as delta x. So if delta x is 0.2, then dx will be 0.2 also. So we can plug these values in. We get 1 over 2 times the square root of 16 times dx, which is 0.2. So we get 1 over 8, and then 0.2, just so we can use fractions, I'm going to write it as 2 over 10, only because I'm doing this part by hand, right? So this is 1 divided by 2 times 4, which is 1 over 8. 0.2 is just the same as 2 over 10. Then we can multiply these two together and get 2 over 80, or 1 over 40. Okay, and just think of, if this said 1 over 4, we'd say 0.25. So 1 over 40 is going to be 0.025. Okay, so remember, we're finding the approximate change in y as x changes by 0.2 from 16 to 16.2. So what we're really finding is this. We're finding that the square root of 16.2 is equal to the square root of 16 plus some change in y. And again, this is the actual change. The actual change in y. Right, so it's the actual change in y as x goes from 16 to 16.2. Well, that's equal to approximately, oops, I need blue there, approximately the square root of 16 plus dy. Again, dy is the approximate, not actual, but the approximate change in y. So we're going to use it as an approximation. And then this is equal to, well, the square root of 16 is 4. dy we just found is 0.025. So we get 4.025. So using differentials, the square root of 16.2 is approximately equal to 4.025. Now, had we used a linear approximation, we would get exactly the same thing, exactly the same. Differentials, we find this little change in y, and then we add it to the square root of 16. When you do a linear approximation, it puts these two together automatically. But had we done a linear approximation, we get exactly the same thing. Now, I will typically say, for any kind of problem, I'll say, approximate this or whatever by using either linear approximations, a linear approximation or differentials. You can do whichever you choose. But if you're going on to Calc 2, it's probably better to concentrate on the linear approximations, because you'll see, as I mentioned, those are really just Taylor series, and you're going to see those in Calc 2. So if you're more familiar with those, it's just going to make Calc 2 easier. All right, so both of these work. You can use differentials or linear approximations, okay, either one. But just to check on the calculator, if we punch in take the TI-8384 and ask it what the square root of 16.2 is, it uses the Cordic algorithm, and it gets 4.0249222359. So again, not too far off. We said 4.025. We could calculate that by hand, and to the third decimal place, it would round to the same amount. So again, fairly close. And of course, remember the differential. When you find this differential, it's the approximate change in the function, right? The change in the function as we go from 16 to 16.2. All right, so let's take a look at example 5. And they ask us to find the differential dy and evaluate dy when x equals 1 and dx equals negative 0.01. Then also evaluate delta y, the actual change in y. So they give us y equals this. Well, isn't that just the same as saying f of x equals this? Function notation. So this is, when they say something like this, we can think of this as just saying y, or we can think of this thing f of x equals this function, right? So y equals f of x. A lot of times you'll say y equals if you're going to graph it. Sometimes you'll be in, you just say f of x equals, but it's the same, right? So we'll think of this as our function f of x, and then we need dy, which we know is f prime of x dx. So we need to take the derivative of this function. So we could think of, just to take the derivative, isn't that the same as x plus 1 to the negative 1? I'm just writing it like this because I don't really feel like doing the quotient rule. And this is really just x plus 1 to the negative 1 power, right? Because couldn't you make this a positive 1, but if you put it underneath a 1, which gets us this. Okay, so then y prime would be, by the power rule, negative x plus 1 to the negative 2, or if you prefer, negative 1 over x plus 1 squared. So, again, that would be the same as f prime of x, because I could have said f of x equals this, right? So we can use this over here for f prime of x. So we can say that dy equals negative 1 over x plus 1 squared dx. And now we can fill this out. So x equals 1, dx equals negative 0.01. So that would mean that dy equals negative 1 over 1 plus 1 squared, which would be 2 squared, which is 4. And then dx is negative 0.01. And this ends up being negative times negative is positive. You get 0.0025. Remember, we found dy, so we're finding the approximate change in the function. Okay, it's not the actual change. The actual change would be delta y, right? The actual change in y. But this is the approximate change in the function. So they said find the differential dy, which we did. Here's dy. We evaluated dy when x equals 1 and dx equals negative 0.01, which is right here. And then they say evaluate delta y. So what that means is find the actual change in y. Okay, so delta y, the change in y, is just equal to the function evaluated at 0.99 minus the function evaluated at 1. And where is this from? Well, originally x was 1, and then it changed by this much. So it changed by negative 0.01, so it went down by 0.01, which gives us this. So this is like the new value, and then, of course, this would be the old value. So to find the change in y, take the new value of y, right, which is the, according to this, x was 1, it went down by this much. So the new value of y is I take this function and I plug in 0.99, and then I subtract this function with a 1 plugged in. All right, so if I take this function, plug in 0.99, I get 1 divided by 1.99, and that is equal to, let's see, 1 divided by 1.99 minus f of 1, well, that's just 1 over 2. Right, again, this is f of x, this is our function, so I plug in these two values, new minus old, to find the actual change. And then this gives us 0.502512568 minus 0.5. So you subtract here, you get 0.002512568, at least to that decimal place. And then this would be the actual change in the function. And again, that's not entirely accurate because we stopped, right? There's actually more decimal places beyond here, but this is, we're just using our calculator. So this is the, what we'll call the actual change in the function. And using differentials, this is the approximate change, and this is what we'll be using to approximate that change. And once again, it's not too bad for a quick calculation like that. And this brings us to our last example. Example 6, we're going to estimate the cubed root of 8.2 using two different ways, a linear approximation and differentials. Once again, on a test or a quiz, I would typically just ask you to do whichever you prefer. For an online class, sometimes I'm a little more limited. I might not, I'm sort of locked in by the test questions that are given to me that I choose from. But definitely in a face-to-face class, I would let you pick whichever one you want. So we'll just do both. So let's first do a linear approximation and then do differentials. Again, the one to concentrate on, really, if you're going to take more calculus, you should probably concentrate on a linear approximation. But just real quick on the calculator, let's see what the calculator gets so we can compare it. The TI 83 or 84 will tell you that the cubed root of 8.2, once again using the Cordic algorithm, is approximately 2.016529675. So we'll just use that as something to compare to. Start off using a linear approximation, and our function here, we've got a cubed root function. So we need to think of a cubed root near 8.2 that we know the answer to. Are you thinking cubed root of 27 is 3? I hope not. It's true, but it's not very close to 8.2. The better one would be the cubed root of 8, right? The cubed root of 8 is 2. So let's center this one for part A. Let's center this. Well, we've got our function is the cubed root of x, or x to the 1/3, and a will be 8, because we know the cubed root of 8. Okay, so we can take the derivative, so f prime of x is going to be 1/3 x to the negative 2/3, or 1/3x to the 2/3 power. And I'm writing it down here because we're going to have to plug a number in here. And when you plug in a number and you have a negative power, it's really not real easy to work with. So I'm just going to put it down here for a positive power. Okay, so we've got f of x, we got f prime of x. Then we need to find f of 8, which of course is the cubed root of 8, which we know is 2. And then f prime of 8, which is 1/3 times 8 to the 2/3. Okay, let's consider this 8 to the 2/3. Well, isn't that the same as 8 to the 1/3 squared? Right, because here you multiply 1/3 times 2 is 2/3. Well, 8 to the 1/3 is the cubed root of 8. That's just 2. So this is 2 squared, which is 4. So this is really 1/3 times 4, or 1/12. Okay, so let's make this a little bigger. There we go. Okay, so we've got f of 8, f prime of 8. So now we're ready to go. We can start working this out. So we know that f of x is approximately equal to f of a plus f prime of a times x minus a. So if we plug this in, our function f of x is the cubed root of x, and we know that's approximately equal to f of a, which is 2, right? Our a is 8, so f of 8 is 2. Then plus f prime of a, which in our case is f prime of 8, that's 1/12. So we go plus 1/12 times x minus a. Now I'm going to make a mistake right here. It happens all the time, and it sends our answer wrong. So what is it about this that's definitely wrong? That, right? This says x minus a. So a is 8. It's real easy to put the 2 here because that's our cubed root of 8, but it's got to be a, right? So we need to make sure that on this point we go x minus a, x minus 8. It's just, I mentioned that because it's a really easy mistake to make. All right, so then if we wanted to figure out the cubed root of 8.2, well, that's going to be about equal to 2 plus 1/12, 8.2 minus 8, right? That's equal to 2 plus 1/12 times, well, that's going to be 0.2, right? 0.2 or 2 over 10. I'm just doing that so I can multiply these two together, and you get 2 over 120 or 1 over 60. Okay, so you might even recognize 1/6 is 0.1 and then all sixes, right? So 1/60th is just going to put a 0 in front of that. So what we're going to get here is basically 2.01 and then 6 is forever, right? 6 repeating, so I'll just round it right here. Okay, I'll round it to the 4th decimal place. And then if we compare this to the answer from the calculator, once again, not too bad for a quick calculation. Okay, so that's using a linear approximation to do this. And we could also use a differential. So for part B, it says they want us to use a differential, so let's do that. So let's go using differentials. This would be good anyway to do them both, so you can see you can kind of compare them. With differentials, we're going to use the point x equals 8, and then delta x will be 0.2, which of course delta x is the same as dx, so this is also saying that dx equals 0.2. Okay, so we'll start with this, and then we know that dy equals f prime of x dx. Well, for us, f of x is once again the cubed root of x, or x to the 1/3. And we've already calculated f prime of x up here, right? We've calculated it up here, so we can do that we can just use that information here. So dy equals 1 over 3 times x to the 2/3 times dx. And in this case, that's going to be, again, we did these calculations already. So once I plug this in, so I have this is dy. Now I plug in 8 for x, I plug in an 8 here, and I plug in 0.2 for dx, because remember dx is the same as delta x. So we would get 1/12, which is, once again, that's the calculation we did up here, right? We plugged in 8 right here and got 1/12. And then dx is 0.2, which is 2 over 10. We're basically doing a lot of the same calculations, so we get 2 over 120, which is 1 over 60, right? So that is our, which we then wrote as 0.0167, right? So this is our delta y. Or sorry, this is our dy, which we're going to use to approximate delta y. So we've got the cubed root of 8.2. We know that's the cubed root of 8, and then plus a change in y as x changes from 8 to 8.2. We know that's approximately equal to the cubed root of 8 plus dy, right? And dy is what we calculated. So this is equal to 2, the cubed root of 8, which is 2, plus 0.0167. So when you add those together, you get 2.0167, which is the same as we got before. So this is just showing, like, whichever way you go, we're going to get to the same spot, the same answer. Okay, and with that, you should be all set to go with section 3.10, linear approximations and differentials. So, like I always say, this just takes some practice, so make sure you put in the practice time. It's the only way to learn calculus. You have to practice. Can't just watch me on these super awesome videos doing calculus. You're going to have to do it yourself, right? I mean, think how nice that could be if you just watch somebody and you could do it. Like you could watch a basketball game and suddenly you're good enough to play in the league. You go over to Detroit Pistons office and say, sign me up, coach. I've been watching a lot of ball games. I'm ready to play. It's the same with calculus. You have to try it. So with that, go ahead and give these homework problems a try. And as always, let me know if you have any questions.